Okay, today we're going to introduce a new topic. The last unit was on interference between light sources or light from two different sources. And just for a quick review, I'm going to do something with, I'll just make a sketch and we'll look at the single slit diffraction stuff that we had going on there. And those are about some distance apart. So I've got two slits there, a slit here and a slit here. And we had that the distance between the slits is lowercase d, so we'll stick with that. So that's how far it is between these things. And we learned about how if you have light going not straight ahead, if the light goes straight ahead and hits a screen, then it will be in phase. The light from the two slits will not have traveled different distances. But if you have them traveling so that light from the bottom slit, for instance, has to travel a little farther from the light from the top slit, they'll be out of phase when we get there to the screen, or when they get there. So if this is the angle theta, you can play around with a little bit of geometry, and you'd find out that this is also the angle theta, and the whole mess arrives because of this path length difference, this little distance right here. And they've been using the letter lowercase delta for that, but it's equal to d sine theta. And it turns out that we will have things will arrive in phase if that distance happens to be equal to one wavelength or two wavelengths or even zero wavelengths if you go straight ahead. But the condition for maxima is that d sine theta is equal to m lambda. And so anytime you've got an integer number of wavelengths for the path length difference, things fit together very nicely again, and that's when you get maxima. And here m is equal to, you can include 0 if you want to, although the central maximum is when sine theta is 0. So if you're going at some angle other than 0, you can't have an m value of 0. But anyway, you can think of it being 1, 2, 3, dot, dot, dot. And you can actually have plus or minus 1 if you want to have negative angles as well. So that would be down in this direction. So it works anyway. And minima happen when that path length difference is equal to m, let's see, I'll go ahead and include 0 here. So m plus a half times lambda. So this would be half integer numbers of wavelengths, 1/2 wavelength, 3/2 of a wavelength, and so forth. And that's when you have complete interference. And then we developed a formula also for the intensity of the light when it was in between maxima and minima. So that's as far as we went with the two slit interference, just about. And we also looked at in class, I showed you a demonstration with 3, 4, and 5 slits. And so you can see those things. Now, as these formulas are written, it seems as if they go on forever. But I want to show you change our view here for a minute. And I've got these are pictures that I took in the classroom when I had, well, it was during COVID actually, but before I retired, and I went out to school one day with my camera, and took a bunch of pictures of diffraction and interference patterns. And this is a two-slit interference pattern. And you can see, if I get my cursed mouse over here, I hope this shows up for you. Anyway, here's the center of the interference pattern. It's just about straight up from the E in interference. The first E in interference is about the center of it. And you can see these things that are kind of evenly spaced, but something else happens, and that is that the pattern fades away more or less to zero at particular points, and then the interference pattern comes back, and then it fades away again, and it comes back. And that's not something that's predicted by the relations that we developed so far. And so we need to do a little bit of work to try and figure out what's going on that could make that happen. Now, I just realized that I switched into the wrong piece of software. This was something I was starting to work on, but that is the picture that we want to see. But I'll go over to, let's see, I'll do a different share and go to, where is it? Here it is. Or is that the one? There we are. Okay. This is the one that I wanted to show you. So there's the two-slit pattern again anyway. And now, today we're going to start considering single-slit patterns. And it turns out that two-slit pattern can be understood if we realize that when you have a single slit, this is a single slit pattern, and this might be the pattern that you get if you just covered up one of the slits from this pattern. So something to notice here. On this one, I apparently didn't have it lined up real great. And I can only see the very first part of this single slit pattern, but you can see that it's bright in the middle, and then it fades to zero on either side of that center part. Here's one that I did a better job capturing. This is another single slit pattern, but it was a slit that was of a different width. And so we'll try to understand how that might happen here. But anyway, you can see in this one that it fades to zero, the single slit pattern does, and then it comes back. You can barely see that coming back part here. Maybe you can't even see it. I'm not sure, but it does come back. This one, you can definitely see it. This is a single slit pattern, got a bright central maximum, fades to nothing more or less, then it comes back, fades to nothing again, comes back, fades to nothing, and so forth. And this is a single slit pattern. And when we go back to that two slit pattern we saw, we can start to understand what's happening here, that the single slit diffraction pattern is what we call those, is overlaid on top of the two slit pattern. The equations we had for the two slit pattern would never fade out, but when you've got that single slit thing going on at the same time, then that two slit pattern fades out, comes back, fades out again, comes back. And that's what's going on in this case. So today we're going to try to understand what's going on with the single slit pattern and do a little bit of math learning about that. So let's change our view back to the other screen. So we can try to understand what's going on with those things. And I'm going to grab another thin sheet of paper, or I'll just. Okay, so now let's consider a single slit that the light is incident on. And think I'll make a fairly wide looking gap on here. So this is a single slit, and we're going to be employing something called Huygens principle. And Huygens was a contemporary of more or less back around the time of Newton. I can't remember exactly what his dates happen to be, but we're going to think about this time our slit width is going to be A. We'll reserve the lowercase d for the separation between the centers of two different slits. So this is just going to be one of the slits. Then we're going to see how we can get interference happening as a result of this. Now, or diffraction is what we'll consider it to be. Huygens' principle is this. And this was in the very first chapter on light, and it was the tail end of that. And we didn't really cover it, but he said that if you have a wave or waves that are traveling along in this direction, that every point on the wave serves as a source of waves that are spreading out in every direction. So you could pick any point along the front of this wave, and it'll be sending waves out in every direction. But he worked through the math and showed that when you have every point doing that, that you still end up with waves overall that are just headed along in that direction. And so that was the idea. So every point on a wave acts as a point source as going in every direction. However, when they do that, when you add them all up, you end up with stuff that's going in one direction. However, and especially if you have an infinitely long line or something that's very long. But when you have something that's no longer so very long, the fact that these things are acting every point along a line between here is acting as a point source means that when you've got a narrow opening like this, the waves don't just stay along a narrow path when they come through here, they spread out from it. And so you have light, if you've got a distant screen over here, you get light on a very long spectrum of things. And it turns out that when you make things narrower and narrower, the light spreads out even more. So shrink this down and it'll cause a wider spreading. So what we're going to think about here is imagine that we pick a point that's exactly 1/2 A up from the bottom of this slit, and then compare the light from that with the light that's leaving from the very top of the slit here. And so if you went straight ahead to a distant screen, the light from those 2 points would travel the same distance. There'd be no path length difference. And so the light would arrive in phase over here, and you could pick a point right underneath that one at the top and a point right underneath that one, and those would travel the same distance as well. And so what you'd have is all of the light that's leaving from this slit when it goes straight ahead travels the same distance to a very distant screen. Remember that the width of these things is going to be fractions of millimeters most of the time, so it's pretty narrow. However, what if that light is going up at some angle theta. So from the straight ahead thing. And again, I exaggerate the angles on here just so we can see so I can draw them and we'll actually see something on here. Okay. Now, that light that leaves up here at the top and the light that leaves at the halfway point, well, there's going to be a path length difference. And that path length difference is going to be delta. And if this is the angle theta, this will also be the angle theta. And remember, this hypotenuse is going to be a divided by 2. And this over a divided by 2 would equal the sine of theta. This ends up being, the path length difference is a over 2 times the sine of theta. And that's the path length difference between the light from the exact middle and light from the very top. Now, I can come down just a smidgen from each one of those, and they'll still be separated by a over 2. And if I go in that same direction, the light from those things is going to be out of, or have a path length difference of a over 2 sine theta. And what I'll find out is that every point in the bottom half of this, compared to every point from the top half, the light from the bottom halves can always be paired up with something from the top, and there will be a path length difference of a over 2 sine theta for that. And so I can match up the bottom half with the top half, and I always get that same phase difference there. Okay, well, when do I get minima? Well, I'll get minima if this distance happens to be half of a wavelength, or 3/2 of a wavelength, or let's see, 5/2. Whoops, forgot the lambda on that one. And so forth. These are minima. Okay, well, let's see. So a over 2 sine theta is going to equal 1/2 lambda, 3/2 lambda, 5/2 lambda. That means a sine theta will equal, multiply both sides by 2, and I get lambda, 3 lambda, 5 lambda, dot, 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 and so forth. So that's our condition for minima, and I can write that out. I can write it as, say, 2m minus 1 times lambda. That way I can let m equal 1, 2, 3, dot, dot, dot. And so, yeah, if m is 1, then I'd get 1 lambda. If m is 2, I'd get 3 lambda, and so forth. So that's our condition for minima. A sine theta is equal to m lambda, but I don't have to just divide it in half. I can divide it in fourths. And so let's see what happens if I divide it in fourths. If instead of being a over 2 sine theta is equal to 1/2 lambda, 3/2 lambda, 5/2 lambda, I could do the same thing with fourths, and light from the bottom fourth would interfere with light from the next fourth up. Then the third fourth that's here will interfere with light from there, and I'll get a minimum again, complete destructive interference. And so I could also say that a over 4 sine theta is going to equal 1/2 lambda, 3/2 lambda, 5/2 lambda. Well, let's see. Then I multiply by 4, and I'd get that a sine theta is going to equal 2 lambda, or let's see, 6 lambda. Let's see, did I miss any? 1/2 lambda. I still got the 1, 2, 3s. Oh, wait, 4 times 3 is 12 divided by 2. Yeah, that's 6 lambda. This one would be 20, 10 lambda. and so forth. And so I filled in some of the even ones, and then you could imagine splitting it into sixths. So what if we split it into sixths? As long as you're splitting it into even numbers of things, it'll always work. You can get this destructive interference equals 1/2 lambda, 3/2 lambda. So 6/3, that would give me 3 lambda. 6 times 3 is 18/2. That'll give me 9 lambda. That's some of the ones that I got before. Excuse me, I got a scratchy throat today. What if we pick up A/8 sine theta? See what we'd get from that one. If I multiplied that by this, I'd have 4 lambda. I'd have a bunch of other lambdas, but I didn't get 4 lambda before. Turns out by splitting it into finer and finer divisions, you end up taking care of every possible integer that can show up. And you get minima when this is the condition. A sine theta is equal to m lambda. And these are the minima. Okay. Now, for the two-slit interference, two-slit pattern, we had d sine theta equaling m lambda for maxima. And so this is different. One slit, the slit width times the sine of theta equals m lambda is when we get minima. With the two slit, it's d sine theta. That's the distance between the two slits is equaling m lambda. That's when you get maxima. So different formulas that look an awful lot alike, but you have to be careful because this one gives you maxima, this one gives you minima. Okay, well, let's try a problem on these things and see what we can figure out from this. Okay, turns out lasers, by their design, produce typically a single wavelength of light, although that's not always the case with cheap solid state lasers that you might buy. But the ones that have a gas in them, and I think some solid state lasers are pretty good too, but some of them aren't all that nailed down. But this one anyway sends out very precise wavelengths, sends it through a 0.3302 millimeter wide single slit. Okay, that's pretty narrow. That's only 33 hundredths of a millimeter is what it happens to be. So pretty narrow. And what's the width of the central maximum on a screen that is 1.505 meters beyond the slit? Okay, well, I'm just going to imagine that we got this barrier and this little dot here is going to represent the slit, and sending light out here in some direction, and the distance here is 1.505 meters. That doesn't seem that far away, but look how narrow the slit is. It's only 33 tenths or hundredths of a millimeter, so it's narrower than a millimeter. This is 1,505 millimeters. So you're going to be something like 4,500 times away from this single slit as it is wide. So, and we'd like to know when we get over to here, what is the width of the central maximum? Well, here's the thing. You'll have a bright spot, and I'm going to make a sketch here that's going to indicate sideways the intensity of the light over here. And it's symmetric either side of the central maximum. And we want to know, how wide is this central maximum here? What is the distance from one minimum on one side to the minimum on the other side? Okay, well, that's the very first minimum that happens. And so here's an angle theta. Things we know for this is that a sine theta for that first minimum is just going to equal lambda. So it'll be m lambda, but m is 1 for the very first minimum. And so we can figure out what the angle theta happens to be. That sine of theta is going to equal lambda over a. And let's see if I think of this little height here as being h, then h over 1.505 meters is going to equal the tangent of theta. So once I can figure out theta, I'll just be able to plug it into there, and h will then equal, actually we want 2h, because that'll be distance from one minimum to the other. That'll equal 2 times 1.505 meters times the tangent of whatever that angle ends up being, and we'll worry about it. So let's figure it out. Well, the wavelength of the light is 632.8 nanometers. That's times 10 to the minus 9th meters. And the width of the slit is 0.3302 times 10 to the minus 3rd meters. So 0.3302 times 10 to the minus 3rd meters. That's going to be sine theta equaling that. So calculator time for this, 632.8 minus 9th divided by 0.3302 times 10 to the minus 3rd. And I get 1.916 times 10 to the minus 3rd, and that's dimensionless. The meters divide out. Okay, that's the sine of theta. If I was working in radians, and right now my calculator's on degrees, but I'm going to switch it over to radians here. And get out of there. I'll just take that thing and multiply it by 1, so I have it back in here. Okay, now if I calculate the sine of that angle, 1.9164 times 10 to the minus 3rd, and do the sine of that, don't know if you can see this or not. Oops, got reflections on here. Sorry about that. Anyway, I get 1.9164 times 10 to the minus 3rd. It's exactly the same thing. Okay, and so the sine of theta is equal to that, and theta, or actually if I calculate the inverse sine of that number, that's what I should have done, but it's okay, didn't change it any. So inverse sine of that number, I get the same thing back again. It turns out for small angles, and I've talked about this before, for theta much less than 1 radian, the angle is equal to the sine of the angle, and it's also equal to the tangent of the angle. If I do the tangent of this angle, tangent of that answer, I get the same thing again. And so I got that the sine of theta was equal to that. Well, I can just replace that or use that to substitute in for the tangent of theta. This is called a small angle approximation. So, and 1.916 times 10 to the minus 3rd is definitely smaller than 1, a lot smaller than 1. So I'll just take the 1.916 times 10 to the minus third and stick it in there. And so the width of our central maximum is going to be 2 times that times 1.505 meters. And I get that 2h is going to be 5.768. And then I can keep 4 sig figs all the way through here. Times 10 to the minus third meters, or 2h is equal to 5.768 millimeters. And so we got lots of precision on there, but that's going to be about that wide, the distance between the tips of my index fingers here. So anyway, pretty small spot on the screen, but it'd be easily viewed. And if you want to bump this up to about 10 meters, which is the distance from the back of our classroom to the front of it, then it'd be spread out 10 times bigger than that. So you'd have about 5.77 centimeters is how wide that would be, which is going to be about that wide centimeter wise. So a whole lot easier to see. Okay, well, let's see if this one is still going to work for us. At some point here, we're going to have to calculate another formula, but this one anyway, got a beam of green light from a helium-cadmium laser is diffracted by a slit of width 0.550 millimeters. Okay. The diffraction pattern forms on a wall 2.06 meters beyond the slit. Okay, so I'm just going to do what I did last time, where this will represent the slit. And we know what the width of the slit is. It's 0.550 millimeters. And then we've got a screen over here, 2.06 meters away. So, and the central maximum would be right here. So there's our screen, 2.06 meters. And on that screen, there'll be a central maximum over there. I probably don't get the heights of these things right. This second maximum is, I don't remember what fraction of the central maximum, but it's down quite a ways anyway. A lot more than I made it look. Okay, distance between the positions of zero intensity, the m equal plus or minus 1, is 4.11 millimeters. So this over here, 4.11 millimeters from one side to the other. And I'm supposed to figure out the wavelength of the laser light. And turned out that kind of laser can make 2 different wavelengths that are fairly precisely defined there. So we'll figure out what it happens to be. So here's theta. And I'll just write down my equation here. A sine of theta is going to equal, for that first maximum, m equal plus or minus 1. That's just going to equal m lambda, or 1 lambda, or just plain lambda. So I have that. And let's see. When it gets all the way over to there, I'll put in my little h here again, the height of 1/2 of that pattern, and h over 2.06 meters is going to equal the tangent of theta. You think I'm going to have be able to use a small angle approximation here? Well, they give me what this thing happens to be. Actually, I can say that 2h over 2.06 meters is going to be 4.0. Yeah, I'll just do this. 4.11 times 10 to the minus third meters. And if I divide by twice that distance, 2h over 2 times that distance is equal to h over that thing. That way I don't have to divide this in my head. I'm being lazy, even though it's 2.055, but that's okay. Anyway, and on the bottom here, I'd have 4.12 meters. So I'll have 3 significant figures, and that'll equal to the tangent of theta. And it looks to me like I'm going to be able to use a small angle approximation here, because this is going to be about 1 times 10 to the minus third. And so, in fact, let's see, 4.11 divided by 4.12. Okay, and I would actually get 9.98 times 10 to the minus fourth for the tangent of theta, and that will equal, that's small enough that that's going to equal the sine of theta, and so I can figure out lambda. Okay, anyway, a sine of theta is just going to equal lambda. So I just take this thing and multiply it by a. So 0.550 times 10 to the minus third meters times, yeah, 9.98 times 10 to the minus fourth. This is going to equal lambda, although it's not going to be, let's see, times. Whoops. It would help if I put millimeters on that first thing instead of oh shoot, what did I do? Oh, I've got all kinds of junk mixed in here. Okay, I would get about let's see, it's 5.489 times 10 to the minus seventh meters. Which is equal to 548.9. I'm not getting either one of those wavelengths here, unless I just punched something in wrong, which is entirely possible. A was equal to that. Huh, I wonder if I copied down this problem wrong, because I get 548.9 millimeters which is far enough off that with as many, or 549 actually, as many sig figs as we've got, I should have been able to do better than that. So, unless I lost a factor of 2 somewhere. Let me make sure I punch this in right. Yeah, that looks right. Okay, so there's something wrong with this problem. I'll see if I can track down that book and see if I got something copied out of here wrong. But I would get this for the wavelength of the light, 549 nanometers. So I'm not positive this is a good problem. Let's see, a diffraction pattern. Okay, this is asking about the intensity of the light. And for this, we need to do some work to talk about the intensity of light in a diffraction pattern. And I'll kind of go back to our picture looking at wherever they were, these things. And so we should be back viewing that single slit pattern again. And these are all different single slit patterns. But something you notice is that there's the central maximum here, and the light comes back, but it's a lot dimmer, and eventually it just fades away completely. And it does that in either one of these images here. These are for different slit widths, and it just fades away after a while. And the intensity formula should be able to predict what's going to happen on this thing. And so I want to show you something. This is going to be making use of a phasor diagram, but it's kind of tricky to try and understand what's going on in this thing. So I'm going to start by drawing. I'm going to imagine in our phase space here that right at the bottom we'll have an arrow representing light from the bottom of the slit, and then I'll draw a kind of well, I don't know, it's just going to be a drawing that's going to represent, let's see, I'm going to imagine taking the light from a whole bunch of different chunks of the slit and representing the light as an arrow. But if I choose a whole bunch of those, the phase difference between light from adjacent slits or adjacent parts of the slit is going to get smaller and smaller. And I'd look at the limit as I go toward, say, 1,000 or 10,000 or 100,000.
You're still on the slideshow.
Whoops, still on slideshow. Okay, let's get back to this thing. Visualizer. Okay, back. Anyway, I'll look at the limit as I'm splitting that slit up into a whole bunch of parts, and what I'll end up with is a circular arc that represents adding together all of those different things. And the length of this circular arc is actually going to be remember we talked about these phase diagrams representing the electric field strength at the screen, at the viewing screen, due to light from these different parts of a slit when we did it before. But here it's going to be, yeah, different parts of the slit is what it is. But the arc length represents is equal to the E0, which is the electric field strength, at center of the central maximum. However, the chord length that we have on here this is going to represent the electric field strength at some different angle direction. And so we'll have to figure out how that works. Now, something that's going to happen here is that this last little bit of the arc here is going to represent, say, the very top of the, actually, it would represent the bottom of the slit. This would represent the top of the slit. This is the part that's farthest out of phase because it had to travel the farthest. And this angle beta here is going to be the phase difference. I'll write it up here. Between bottom and top of the slit. Well, what's that going to arise from? That phase difference will equal, I'll have A sine theta is going to be the path length difference. If I divide A sine theta by lambda, I have the number of wavelengths of light that fit into that path length difference. And if I multiply it by 2 pi, then I get that this is the phase difference. And so that's actually what beta is equal to. So it's little beta there is going to stand for a whole bunch of stuff that I'm going to have here. Now, the radius of this arc, remember this arc length was equal to E naught. The radius of the arc, turns out this angle up here is also going to equal beta. And so this radius is equal to the arc length divided by the angle. So we'll have that. And we want to know what the length of this thing happens to be. Okay, that'll be the electric field strength. I could think of that as E as a function of beta, I guess. Now, I'm going to take this and split it in half so that this will be beta over 2, and this angle will be beta over 2. This is all abstract a zillion different ways, but this is going to be perpendicular. This will be perpendicular. This length divided by the radius here is going to equal the sine of beta over 2, and this is 1/2 of E of beta. Okay, and the total thing will be all the way across there. Well, that 1/2 of that electric field strength of beta divided by E naught over beta. This E is a function of beta. This is E naught of beta. That's going to be the sine of beta over 2 is what I'll have there. And if I multiply out from underneath by that thing, I'll have that 1/2 E as a function of beta will end up equaling sine, actually it'll be E naught sine of beta over 2 divided by beta. I've got, yeah, multiply that out from underneath. And if I multiply both sides by 2, I find out that the electric field at an angle beta that's determined by the angle theta. So this is complicated. Anyway, E of beta will end up being 2 E naught sine of beta over 2 divided by beta. But if I multiply top and bottom by 1/2, the way that you usually see this is it's E naught, and then you have the sine of beta over 2 divided by beta over 2. And so you've got the same argument top and bottom on this thing. And that's just the electric field strength. Now, it turns out the intensity of the light is equal to, I'm just going to call it C times E squared. So we would take this thing and square it, and we would get C times E naught squared, and then we'd have sine squared of beta over 2, complicated math, I know, divided by beta over 2 squared. And this constant, C times E naught squared, would be the intensity of the central maximum. And so this ends up being, and we could call that I sub 0. I sub 0, the intensity at the central highest point, times sine squared of beta over 2 divided by beta over 2 squared. Now, it may not be obvious, but looking at this thing, there's a part that varies sinusoidally, which means it's going to go up and down. It goes with the square of the sine, though. So it never goes negative. And if you graph the square of a sine wave, you get something that looks like this. It just keeps going up and down. It's got a maximum value of 1 and a minimum value of 0. That's what a sine squared function looks like. So that explains the coming in and out. But you're dividing by this beta over 2 squared. That's something that keeps getting larger and larger with the increasing angle theta, and you can't go past theta 90 degrees for this thing. And so this keeps getting bigger and bigger, and that's why those subsequent maxima end up getting less and less, and after a while you can't even see them anymore. So this formula explains all of that stuff in one fell swoop, but it was hard to get to it. And I don't expect you to be able to do that necessarily, although you could work through it if you like it. So anyway, let's come to this problem here, and keep in mind the intensity is going to be I naught sine squared of beta over 2 divided by beta over 2 squared. Sometimes you see this whole thing wrapped in parentheses and square the whole works. So we want to know the fractional intensity I over I naught at a point on the screen, 4.10 millimeters from the center of the principal maximum. Okay, now remember where beta came from. It's equal to A sine theta over lambda times 2 pi. So let's just remind ourselves of that. And diffraction pattern formed on a screen 1.20 meters away from a 0.400 millimeter wide slit. So this is A. Monochromatic light, 546.1 nanometers. So there's lambda. And we ought to be able to do this. 4.10 millimeters away. So I think we can figure out that angle theta. Going to be 4.10 times 10 to the minus third meters. Here's theta. And we are 4.1, what? On the screen. Wait, oh, 1.20 meters. That's what that one is. Okay. So now I can figure out what theta happens to be. I can figure out beta. Actually, beta over 2 is going to be a sine theta over lambda. Instead of 2 pi, I'll just have pi here. And so that's what beta over 2 will be. And then I can do the sine of beta over 2 divided by beta over 2 squared. So, all right, let's plug in and see what beta over 2 happens to be. It's going to be A is 0.400 times 10 to the minus third meters times the sine of, well, let's check out the tangent of this angle and see if the sine of theta is going to be equal to it. Okay, so tangent of theta, I think it is 4.10 times 10 to the minus third divided by 1.20. Okay, and I get 3.42 times 10 to the minus third. And that's small enough that that's also going to equal the sine of theta. And just to verify it, I'll stick it into my calculator and calculate the sine of that angle. I've got my calculator in radians for this, which, by the way, you have to. If you're monkeying with degrees, it's going to be way cockeyed. Anyway, the sine of that, and I get exactly the same thing back, 5 significant figures. So, and I only need 3 on here. So this formula was supposed to have a sine of theta in it. So that'll be my 3.42 times 10 to the minus third, and sines are dimensionless. And on the bottom, the wavelength, 546.1. Uh-oh, the dog's in trouble. Times 10 to the minus ninth meters. So there's the lambda, and then I multiply by pi. And so I can just do that. Okay, 3.42. That number, need this one. Whoops. How did I get that? E. I don't know what I pushed. I'm not sure I did that right. Whoops. Put the decimal point in the wrong place on that. Oh well, I can fix it. Oh, rat. I'm all fouled up now. I made one mistake. I'll have to start over again calculating this, but 0.4 E minus 3 times. Okay, actually I get 7.82 3 sig figs, 7 radians. Okay, so what I want is I over I naught. And that's just going to be the sine of this angle. No, I can't use a small angle approximation on this now. So I'll have sine squared of, that's beta over 2, 7.87 radians divided by 7.87 radians, which are dimensionless, squared. So that will equal, oh, let's see. Second answer squared. And I get 1.61 times 10 to the minus 2. So the intensity is going to be about 1.61% of what it is at the center maximum. So anyway, there's one that uses intensity on there. And I think I'll stop there. I don't have time to do another problem. But what we've introduced today is first the idea of single slit diffraction, and that's overlaid on top of two slit interference. And that's why the two slit interference fades away after a while, and fades away, comes back, fades away, comes back. And then we learned the intensity of the single slit pattern compared to the intensity of its center. So that'll be useful. And we have a lab, might even do it Tuesday, actually, because Tuesday we'll be doing a lab you don't have to turn in. Yeah, it's one where I give you a bunch of data, and from that, you do some number crunching to try to figure out what would be the slit width and slit separation to produce that data. So, and I've got a bunch of data points, and I think I've got them in a form where you can just open up an Excel file and start experimenting with it. So, any questions? This was pretty challenging stuff, actually. So I'm going to stop the recording.